All right, the next speaker is Art Benjamin. He's talking about the combinatorialization of linear recurrences.
Okay, this is joint work with Jennifer Quinn and former undergraduate Halcyon Derks. Now we all know how to solve linear recurrences, right? I mean, recurrences that's of this form. You find its characteristic polynomial, say it's a kth degree recurrence. You find the characteristic polynomial. If you're lucky and that polynomial has distinct roots, you say, okay, then I know there must be constants C1 through Ck, so that my closed form to the recurrence is a linear combination of those roots raised to the nth power, where those coefficients depend on the initial conditions. Okay? So for example, the goal of this talk, by the way, is to prove this and more combinatorial. So for example, the famous Fibonacci recurrence has characteristic polynomial x squared minus x minus 1. Those are its roots. And so, anything that has that recurrence is going to have a closed form that looks like that. In particular, if f0 is 0 and f1 is 1, we get the familiar Binet formula. Okay? So my goal is to prove this and more through combinatorics. Let's start off with second-order recurrences. Then I'll show you third-order recurrences. Then arbitrary with distinct roots. And then finally, what happens if you have repeated roots. Okay? That's what we're going to do. So second-order recurrence looks like this. X squared minus, with coefficients a1 and a2. There's the characteristic polynomial. Okay, let's say it has distinct roots, R1 and R2. I want to show that its closed form looks like that. Now, typically, when, since we're going to do this combinatorially, you see a recurrence that looks like that, you ask, well, what's it counting? Well, the traditional model is you say, well, Hn is counting tilings of a strip, a board of length n, using squares and dominoes, where squares have length 1, dominoes have length 2, except we're going to give our squares a weight of a1, we're going to give our dominoes a weight of a2. That's the traditional model for these recurrences, but that doesn't get those roots into the picture. So instead, we're going to do a more colorful model. Imagine now we have two different colors of squares. We have light squares that have weight r1, dark squares which have weight r2, those are the roots of the polynomial. And our dominoes will have a weight of negative r1, r2. The weight of a tiling will be defined to be the product of the weights of the tiles. Let's do an example. Okay? Before I do that, there's an exception. Initial tiles get a different weight than the other tiles. What are the weights? If the tile at the very beginning, a square on cell 1 will have weight C1, R1 if it's light, C2, R2 if it's dark, and a domino gets weight negative C1 plus C2, R1, R2. Consider those, we'll determine what those constants are later when we need them. Okay? So for example, here's a tiling, a light square, a dark square, a domino, light, light. You see what their weights are, multiply those weights together. That's the weight of that tiling. I'm going to let Wn be the total weight of all tilings of length n. I claim Wn, the total weight of all these tilings, satisfies the same recurrence as H sub n. Okay, that's what we want to show. So let's see that. Well, what's the total weight of all the tilings? Well, consider the last tile. The last tile could either be a light square, in which case that tile has weight R1 and it's preceded by a tiling of length n minus 1, or it ends with a dark square, or it ends with a domino. And that domino has a weight negative R1, R2, preceded by a tiling of length n minus 2. So the total weight is this. But wait a second, that's the same as A1 Wn minus 1 plus A2 Wn minus 2 because they were the roots of the polynomial. So we know what the sum of the roots are. We know what the product of the roots are. So this has the same recurrence, satisfies the same relation as our problem. But then why do you get the Binet formula, right? How does that give us that? All right, so here's the combinatorial proof. Here's where the fun begins. All right, I'm going to say that a tiling is impure if it contains anywhere in the tiling a domino, anywhere, or it contains two adjacent squares of opposite color. So if you have this in your tiling, or light dark, or dark light anywhere, then your tiling is impure. Needless to say, most tilings are impure. What I claim is that the totality of all, if you take the sum of all impure tilings, you're going to get 0. All right, let's see. So here's a typical tiling, all right? And here's the first impurity. This is the first place where I either see a domino, or a light dark, or a dark light. Now there are two situations we'll look at. Either the tiling does not start with an impurity, or it does start with an impurity. Let's look at the case where it doesn't. What do we do here? We need to find something like a sign reversing involution. I like to say we want to find a mate of opposite weight. That's kind of poetic. Find a mate of opposite weight. How do we do that? Well, we take our tiling, we clone it, take that first impurity, erase, and replace with what? With a domino. Yes, because by replacing with a domino, the weight, instead of being R1, R2, is negative R1, R2. Now, does this go backwards? How do I know, do I go light dark or do I go dark light? I have to go light dark because this is the first impurity. So I look behind me, all I see are light squares. I have to make that a light dark, because if it was dark light, that wouldn't be the first impurity anymore. It would be over there. So there's only one way to go down, one way to go up. Everything else is the same, so the weights sum to 0. So we found our mate of opposite weight. If we did not start with an impurity, right? I had to have stuff behind me for that argument to work. What if we do start with an impurity? Well, in this case, and it almost rhymes, we find a trio that sums to 0. All right? So there are 3 ways you can start with an impurity, right? You can either be, well, so I just cloned them, but now let's erase and replace light dark, dark light, or domino. And notice, no matter arbitrarily how I define those C1s and C2s, those weights, those 3 weights, sum to 0 for any values of C1 or C2. Okay? So, the impure tilings do sum to 0. Therefore, since Wn is the total weight of all the tilings, all we have to look at is the total weight of all the pure tilings, right? Because all the impure tilings, they kill each other. Right? Okay, so what are the pure tilings? How can you be pure? Either all light squares or all dark squares. No dominoes anywhere, no color changes. The weight of all light squares, that's going to be C1 R1 to the n. The weight of all dark squares, that's C2 R2 to the n. Therefore, the total weight is C1 R1 to the n plus C2 R2 to the n as desired. Okay? So, that's the, now, and then of course the initial conditions, right? C1 and C2 are arbitrary. Wn and Hn, they satisfy the same recurrence. So as long as they satisfy the same initial conditions, they're gonna be the same. And since there's a unique solution to that, just as in the usual way, we can find C1 and C2, which doesn't. Okay, so that's the case. We now have second-order recurrences explained combinatorially. All right, what about third-order recurrences? All right, now we have a cubic as our characteristic polynomial. We want to show that it satisfies that condition. All right, so now, again, I'm still assuming there are 3 distinct roots. So let's say R1, R2, and R3. That gives us 3 types of squares. We have 3 types of dominoes this time. And you'll notice I combined red and blue and got purple, red and yellow, got orange. Okay. Anyway, so that's so we have 3 types of dominoes. Those are the negative weights. And this time, since the third order recurrence, I have a trimino, a tile of length 3, and its weight is R1, R2, R3. All right? Oh, and the initial tiles, they have the same weights as before, except they have those C's in front to get things to work out at the end. All right. Just like before, the total weight of my tilings, Wn is the total weight of my tilings. Here, ends with a square of one of three colors, ends with a domino with one of three types of weights, ends with a